Okay, I'm going to analyse this truss here. It's a trapezium shape with members at nodes A, B, C, D and E. They're the nodes. We've got our supports, we've got a pin joint. So this truss is connected to a wall at C. And you've got a roller joint at E. Got a force 2000 newtons being applied at A, a force 1000 newtons being applied at B, and I've got my dimensions on the outside, 12 by 12, to depth 8 metres, and you've got 6, 12, 6 metres. So I'll just draw a free body diagram down here, and I'll keep on adding to this diagram what I find out. So I've got 2000 as a definite, got 1000, that's A, B, C, D and E. Now if I was holding down at point C and I was imagining these two forces are rotating this truss, it will go around anti-clockwise. In order to stop it from going around anti-clockwise, to put it in equilibrium, this reaction here has to be pointing upwards so that we've got a restoring moment, clockwise moment, and we'll call that AY. Now if we held at E, again we've got these 2000, 1000 trying to rotate this truss. So you have to try and think, okay, well what type of horizontal reaction have I got? It's likely that you've got a CX heading off in that direction. And I'll guess also that I have a CY going upwards. Now there is an AX, however the theory says that the friction is 0 at E, so it's 0 newtons for EX, so you could write down that EX equals 0. I'll just draw this out again. This is the page I'm going to be doing my calculations on. 2000, 1000, I'm saying that CY is going upwards, CX is going to the right, and I think that AY is going up, A, B, C, and D, E. Now you'll find that you'll end up drawing this truss a number of times and each joint a number of times to try and sort of work out what you have. So one, draw the free body diagram. The next thing that you'll be doing is working out what the reactions are using the external forces on the truss. So you're actually ignoring the forces that are in the members themselves and you're just looking at external forces. So we've got 2000, 1000, CY, CX and EY. Now we've got 3 equilibrium equations. Sum of moments around any particular point is 0. Sum of forces in a horizontal direction is 0. Sum of forces in a vertical direction equal 0. And the formula that you've been introduced to so far is moment equals force times distance. Now in terms of what you've seen so far to date, you've seen when you have a beam with 2 reactions and a point load up here. If you were to take a moment about that point, it would be the force F times by the distance D. And and you've also got this reaction, the force F times by the distance. Now it's always the perpendicular distance to the particular force. So if you're taking moments about this point, if there was a force being applied here at an angle, whenever you're taking moments about a particular point, you've got to take the perpendicular distance to that force. If there's another force being applied to this beam, this is a beam. If you have a force, the perpendicular distance from this point here is that distance there, so that would be a D. Now that's important when you start considering forces for a truss. This is a complicated example where you've got forces in both horizontal and vertical directions. So I'll show you how you can work out our unknowns. So we've got AY is an unknown, CY is an unknown, CX is an unknown. Now the way that we remove unknowns is by taking moments about the point that they pass through. So if I wanted to remove AY, I would take moments about E. That would leave me CY and CX. If I wanted to leave AY, I would take moments about C. So even though that CY is passing through that point, it's 0. So a moment is whatever CY is times by 0. Because CX is also passing through this point, you also ignore CX. So to work out what AY is, the first thing that we'll do is work out the reactions, and we'll try and find AY first. So sum of moments around C. So again, you're just trying to imagine that you've got a hold at this point C, and what forces are taking me around C in an anti-clockwise direction, which are taking me around in a clockwise direction. So looking at my diagram up here, I've got a force 2000, so that's my first one, 2000, and from that point you've got a perpendicular distance of 12 plus 12, so it's 24, and I'll put my distances in brackets. So that there is 12, and that's 12. Got 8 meters down there. So we've got 12,000 going around anti-clockwise. Now you need to say which way your positive is going. So I'm saying that anti-clockwise, I'm making everything positive. Now my next force is my 1000. So I've got 1000. It's sending everything around in an anti-clockwise direction. And the distance from point C is 12. So times by 12. Next we have AY. Now AY is pointing upwards, and it would be sending our truss around C in a clockwise direction. So it's going in a minus direction, AY, and the perpendicular distance from point C is halfway along there, so that's 6 meters. Sum of moments around C equals 0. The only unknown there is AY. Using your calculator, you'll find out that AY is 10,000 newtons, and I've guessed the direction of it correct, going upwards, because this is a positive number. What I'll do, I'll just add AY to my diagram down below here. So we've got AY equals 10,000, and my direction is definitely upwards. So now I know what AY is. You can take moments about a particular point to remove other unknowns. We could take moments around this point here. Now because CX is passing through it, you can ignore that. because EY is passing through it, we can also ignore that. And that would leave us with our 1000, our 2000 and the CY. So you can take moments about a particular point to remove unknowns. And the idea is that you sort of leave one unknown within your equation to try and work out what it is. But to show that the equilibrium equations apply, what we'll do, we'll look at the next one. Sum of forces in an x direction, 0. You know, and again, you've got to sort of say a certain direction will be positive. So in terms of the horizontal forces, the only force that we have is this Cx. Cx. And have we got any other forces going the other direction? Again, at AY, there's a roller joint, but that will give us an Ex of 0. So Cx is 0. And we can look at all of the external forces also in a vertical direction. And I'll say that everything going up is positive. So taking each of the forces, we've got 2000 coming down, so that'll be minus 2000 because all the positive ones are going upwards. We've got 2000 coming down, we've got 1000 coming down. We've got this 10,000, that's going upwards, so we've got plus 10,000. And then we're saying that CY is going upwards, so I'm saying plus CY. All of that will equal 0. Now CY ends up being minus 7,000 newtons. Now I'm guessing that CY was going upwards. Now because it's come out as minus, it means that I've guessed the direction of my reaction wrongly. So CY is actually 7,000 newtons downwards. So I'll draw these onto my free body diagram. I've got Cx equals 0, and my reaction is not going upwards, my reaction is actually going downwards, and that's 7,000. I'll just tip X out. That. So now I've got my reactions. Now that I've got reactions, I can work out what the the forces are within each of the members themselves. Now I've got the dimensions, you know, the 12 meters, 12 meters. We've got 8 meters, 6 meters, 12 meters, and 6 meters there. When we come to work out the forces at particular points, we need to know what the angles are. So if I try to work out what this angle is here, we'll call that beta. You use your trigonometry to try and work out the angle itself. So we've got this AB, and you've got your AD. That distance down there is 8 meters, and you've got 6 meters there. So you've got your angle beta. And you can use whatever method to try and work out what beta is there. You know, I've got the cat sat on an orange and hurt himself. So I've got an opposite the angle and adjacent the angle. So I'm going to actually work this TOA, T-O-A. So tan equals opposite over adjacent. And working with that, I work out that my beta, when you do your opposite 8 divided by adjacent 6, inverse tan it, you end up with 53.13 degrees. That's the angle there. So that's the only angle that I'm going to be working with to work out the members themselves. So on reactions, what I've done, I've worked out the angles the second thing that we're going to be doing is working out each joint. So you can start at any joint as long as you know as long as there's not more than two unknowns at a particular point. So if we look at A first, so 2 members, and we look at joint A first. So joint A, we've got AB along there, we've got AD, and then we've got A here, and we've got 2,000 coming downwards. Now if I've got 2,000 coming downwards, in terms of F, the force in AD, if I'm trying to keep this point in equilibrium, because you've got 2,000 coming downwards, FAD would have to be pointing upwards. Okay, so 2,000's coming down, trying to keep that in place, so we've got FAD should be pointing upwards. We've got FAB. Now because FAD is pushing this point to the left, FAB, in terms of the force, is going to the right. So this is where we're sort of almost like working with vectors. So we've got joint A, let's analyse this. So we'll look at sum of forces. You can't do sum of moments about a particular point because it would cancel out the unknown. So we don't know what FAB is and we don't know what FAD is. So we can't do the sum of moments. We look at the sum of forces in an x direction, and that will equal 0. So what have we got? We've got FAB and we have FAD. Now FAB is in a horizontal direction. FAD, you have to take the horizontal component of FAD. So if we had this angle here, so we said that angle there was 53.13. In terms of the horizontal component of that, you take the cosine 53.13. So now we've got an equation with two unknowns. We can't actually work anything out with that. So let's look at our forces in a y direction. That will equal 0. So we've got 2,000, so we're saying like everything that's going downwards, we'll say that's a positive. So we've got 2,000, our force about this point. And then going upwards, we've got FAD. And in terms of how much of this FAD is acting vertically, and again you got like this 53.13, so it's FAD, and it's opposite, so it's sine 53.13. That all equals 0. Now the only unknown that we have is FAD. So we got, what we're going to do is take the FAD over that side, so we've got 2,000 equal FAD sine 53.13. FAD equals 2000 divided by sine 53.13, and that equals 2500 newtons. So we now know that FAD is 2500. The arrow is pointing upwards, and what you'll find out is that when you come to draw your arrows, FAD here, we've got, when you have your arrows pointing outwards, they're in compression, and when you have your arrows pointing inwards, you'll find that your members are in tension. So we'll put a C after FAD. Okay, so we've just worked out what FAD is. So FAD is 2500, worked out from this equation here. If we put our FAD into this here, so if I put FAD into there, I can work out what FAB is. So FAB equals FAD's 2500 cos 53.13, and you'll find that FAB equals 1500 newtons, and you can see here that FAB, it's pointing inwards, so it's in tension. So I'll add these to my diagram. So FAB, draw that in black now, so I know that it's going inwards, and I've got 1500 in tension, and I've got my FAD, my arrows were pointing outwards, that was 2500 in compression. Okay, so far we've got our EY, our reactions, just worked out what FAD is, just worked out what FAB is, so we know what both of them are. So we've worked out the forces in them two reactions, in those two members, sorry, and we can now move on to another joint. And it's up to you where you want to move. We've just worked out A, we can move to B. The problem is that moving to B is we know what AB is, but we don't know what BD is, we don't know what BE is, we don't know what BC is. So if we analyse this joint, you'd have three unknowns. You can only analyse a joint with two unknowns. We know what this AD is, so we can move next to joint D. So we're going to move to this point here. So joint D. I draw in pencil first, so we've got AD, BD. Okay, so I've worked out that my AD, the arrow is pointing outwards up here, so therefore it's pointing outwards down here. So this is joint D. I've got that member there. Now this is where, again, you've got to try and guess which way. Oh, just realised that we're missing a bit here. So again, we've got FAD, I know that was pointing outwards towards A, so if it was pointing outwards towards A, it's pointing outwards towards D. We've got my FDB. If you looked at the forces in a vertical direction, and if you wanted to try and keep D in that location, you got FAD pushing down, that was 2,500. Therefore, FDB must be pushing upwards. I don't know what that is yet. Now if I've got this force pushing to the right, this force is pushing my dot to the right, therefore I can safely say that FDE is pushing to the left. So what I'm saying just from these arrows here is that when I draw this in, I know that FDB is going to be in tension, and I know that FDE, because the arrows are pointing outwards, it's going to be in compression. I'll scribble them out so it's not too confusing, because we're not looking at the joint, at the forces at this point or that point, we're just looking at them at point D. Okay, we've got an angle of 53.13 in there. We look at the sum of forces in a vertical, we'll call that X direction. We've got our FAD, and how much of that diagonal is acting in a horizontal direction. So how much of that, if you rotated it round, would be acting in a horizontal direction? It's adjacent to the angle, this 53.3. So it's FAD cosine 53.13. We also have FDB, so I'm saying everything that's going in this direction is positive, so we've got plus FDB. How much of this FDB is acting horizontally? It's cosine 53.13. FDE is also acting horizontally, it's minus FDE. That all equals 0. Our problem here is that we've got three unknowns. We've got FD, AD that we know is 2,500. We don't know what DB is, and we don't know what FD is. So let's apply another equilibrium equation. Sum of forces horizontally equals 0. So we got, and we'll say everything coming down is positive. So we got FAD. How much of this FAD is acting vertically? It's opposite the angle, so it's FAD sine 53.13. Our FDB is going upwards, so it's minus FDB. And again it's sine 53.13. FDE is acting perfectly horizontal, so it's not included in a vertical calculation. So all of that equals 0. Now FAD, we know that's 2,500. So we've got sine 53.13 minus FDB sine 53.13 equals 0. You can find out from this equation here what FDB is. FDB equals 2,500. FDB, the arrows are pointing inwards, so that it's tension. Put FDB into this equation here, and you can work out and we know what FAD is, so we know what FDB is now, we know what FAD is, 2,500, and you can work out what FDE is. FDE equals 3,000 newtons. FDE, arrows are pointing outwards, it's in compression. Okay, we'll add this information to our free body diagram. So we've just worked out from joint A, we worked out what these two are. We've just moved to joint D. We said that the arrow was going this way, so we've got both of them coming in like that. So FDB is 2,500 in tension. FDE, we've just worked out what that is. It was 3,000 in compression. Arrows pointing outwards. Right, need another piece of paper to work out the rest of the joints. Now we could move to B because we've got two unknowns, BC and BE, or we could move to E because we could work out BE and AC. We'll move to joint B next. Okay, I'll just draw my diagram out again, just quickly. Got 1,500. Got my force. 1,000. My force. 2,000. 2,500. Put it inwards, 2,500. So we're going to look at this joint B. Joint B. I'll just draw that a bit bigger. So we've got our obvious 1,000 coming down. Figured out that my member down there, the arrow is pointing downwards. That's the BD, it's 2,500. And I know that my FBA is 1,500. Now looking at B here, if we looked at the forces in this direction, if we looked at them vertically, we've got a force coming down here and a force coming down here. Now in terms of trying to work out the direction of F, B, E, I'm guessing that it's going upwards. Now if you looked in a horizontal direction, all of the forces are pointing to the left. You ignore this 1,000 because it's come straight down, so you can guess that your BC is going to the right. So we're trying to work out what BE is and what BC is. So let's look at our sum of forces. Sum of forces in a y direction equals 0, and we'll say that everything going down is positive. So trying to keep this node at B still, we've got 1000 coming down. We've got 1500, but that's purely horizontal, so we ignore that. BC is also horizontal, so we ignore that. So let's look at this force here, that's heading downwards, so it's plus BD. And how much of that BD is acting? Now this is our angle 53.13 again. So I'll draw this out. So we've got the BD of 2500 with an angle, and how much of that is acting downwards? So if you can imagine, got a 90-degree triangle, 2500 there, it's opposite the angle, so it's sine, so BD sine 53.13. We've got our BE is going upwards, so it's minus. So BE sine, and this angle here is also 53.1. 53.13, and all of that will equal 0. BD is 2500, where BD equals 2500. So the only unknown that we have is BE, therefore BE equals 3750 newtons. BE, the arrow is pointing outwards, which is compression. Next, we look at the sum of forces in an x direction, where we say everything going that way is going to be positive. What have we got? We've got FBC. Going the other way, we've got BA 1500. We've also got this BD going to the left, 2500 multiplied by cosine 53.15. So the 2500, how much of that is acting horizontally? So you've got 53 here. It's cosine the angle. So imagine 2500 is the hypotenuse. So it's adjacent. And you also have this BE heading to the left. BE we've just worked out is 3750 cosine 53.13. All of that equals 0. Work it out. BC equals 5250 newtons. We've said that BC is, the arrow is pointing away from the node, so it's pointing inwards, tension. So we'll draw these on to our diagram. So we got BE pointed outwards, 3750 C. We've got BC, just worked out that it's pointing inwards, that's 5250, and tension. We can move on to joint C, which I'm going to leave till last. So we can do a check there, or you can move on to E, because there's just one unknown left. So joint E, so we just worked out what BE is, and BC. To draw joint E, let's have a look, see what we have. So we've got joint E, draw that again. Got joint E there. We've got 10,000 on that joint. We've got this EC. We also have B, E, and we have D, E. And DE we've already worked out, it's heading to the right, it's 3,000. We've all got BE is heading downwards, that's 3,750. We don't know what EC is, and we know what that 1,000 is. So now we're working with joint E. If we look at this joint here, we've got DE's pointing to the right, BE's pointing to the right. To stop E from moving, AC is going to be pointing to the left. So the arrow is pointing outwards. So you can see that AC is going to be in compression. So if we look at the sum of forces, and we see that everything going to the right is positive. We've got EC, it's going to the left, so it's minus, and it's cosine 53.13. Just to show again, this angle here is 53.13. Imagine you have a triangle where EC is the hypotenuse. How much of that is acting in a horizontal direction? So how much of that force is acting in a horizontal direction? It's the hypotenuse times by the cosine, the angle. So we've got AC, we've got 3,000 from DE, which is acting perfectly horizontal, and we have 3,550 from BE, and that's acting cosine 53.13. All of that equals 0. AC equals 8,750 newtons. The arrow looks like that. It's in compression. Now the last thing that we do is a check. So if I just add 8,750, both pointing outwards. If we look at our last joint, that's C. So at C, we've worked out that we've got 5,250. Going this way, we've got our CX. We've got 7,000 coming down, which is our CY. And we've got what we just worked out, 8,750. So all of that's at point C. So if we do our check at joint C, first we'll sum the forces in an x direction. everything going that way is going to be positive. So we've got this 5 to 50 going to the left, so it's minus. We've got this 8, 750 going to the right, so it's positive. And in terms of how much of that acts horizontally, you've got the angle again, that's the hypotenuse, it'll be cosine 53.13. You've got Cx in there, but we worked out that Cx is 0, so we can just ignore that. Equals 0, and what you'll find is that does come to near enough 0. Sum of forces in a y direction, we'll say that everything going upwards is positive. So we've got minus 7,000 coming down, plus our 8, 750 going upwards. How much of that is acting upwards? It's sine 53.13. All of that equals 0, and you'll find it's close enough, therefore OK. So the last thing that you'd be doing is just be drawing out the forces that you have in your members. And the next step would be to design those members to cater